Okay, thank you very much for inviting me to come and talk about what we know so far about the really devastating earthquakes that we saw in Turkey and Syria a few months ago. I think, just like everyone else, my heart goes out to everyone who was affected by these. It's probably, since I became a seismologist, the most devastating set of earthquakes that I've ever seen. But what I'm going to focus on today is some work that I've been involved in, but also mostly incorporated some of the preliminary results that have been shared in preprints and social media to really highlight what we understand so far about this set of earthquakes. So there are two really sort of striking images here of the earthquake. Here we see a tree that's just been sheared by the surface rupturing fault crossing this tree on the left, and on the right here we can see this vehicle track here on the right, which has been offset by something like 7 to 8 meters. So it's a huge amount of displacement. For this talk, I was asked to briefly talk first about Seismica, which is a new diamond open access journal in seismology and earthquake science. So what I mean by diamond open access is that it's both free to read and also free to publish. So this is a community-led journal that's trying to offer some a new way of publishing, or a new option for people to publish in, scientists to submit their work to. And we cover a wide range of disciplines in seismology and earthquake science. And so we have a special issue on the Kahramanmaraş Turkey earthquake sequence. Again, another really striking photo of the fault offset here. So this is a special issue which will be open until February 2024, and we've already had 2 papers published in this special issue, which I'm going to summarize also here. For other sort of geoscience fields, which also have diamond open access journals, I recommend looking at our sort of sibling journals of Tectonica, Volcanica, Sedimentologica. So there's a huge sort of push for these new community diamond open access journals in geoscience at the moment. But Seismic has been very, very successful so far. We've received over 60 submissions in total, with about 20 of those published. So in terms of what's been happening in Turkey and the Middle Eastern area, this is a map of the main plate boundary faults in Turkey and the strongest earthquakes that have been recorded there in the past. So I think before the most recent earthquake, when people thought about large earthquakes in Turkey, the Northern Anatolian fault zone was the one that received the most attention, particularly this sort of apparent westwards migration of large earthquakes over recent decades towards the Istanbul and Marmara Sea area, particularly with 2 large earthquakes in 1999, the magnitude 7.2 and the magnitude 7.6 Izmit earthquake. The Eastern Anatolian fault has been a bit more seismically quiet, but these are instrumental records going back, only about 100 years. So we're obviously missing some of the larger earthquakes here in past centuries. But from sort of paleoseismological evidence, historical written evidence, that we do know that there have been some large magnitude 7 earthquakes along the Eastern Anatolian fault zone. So this map is sort of oriented roughly with west towards the top of this map. And there have been, in recent centuries, magnitude 7 earthquakes rupturing these sort of specific segments from the south to the north. And so this map is from this paper by Güvercin, who said that there was potential for a magnitude 7 to 7.4 earthquake in the future, given that these fault segments haven't ruptured for several centuries. In fact, from GPS measurements, a study looking at slip rates along the Eastern Anatolian fault, the study recognized that there was a slip deficit of about 5 meters along these segments. And so this was only published last year, and they said in this paper that these unruptured segments have the potential to produce an earthquake of magnitude 7.7, which is obviously close to what we saw Obviously, they couldn't predict those earthquakes in space and time, but it was known to be a region of high seismic hazard. Essentially, what we saw in the recent magnitude 7.8 earthquake is that several of these fault segments, this 1893 segment, 1795 segment, and 1872 segment, all went in one earthquake. And so a new preprint by Links and Mengetor has basically classified this as a sort of once in a 1,000-year multi-segment rupture, as what might be classified as sort of a seismic supercycle. So rather than individual segments go in every sort of 1,000 years or so, you actually have cascade and rupture along all of these segments, which generates a much larger magnitude earthquake. So what actually happened on the 6th of February? We had two earthquakes, a magnitude 7.8 to 7.9 earthquake in the early hours of the 6th of February. And then just a few hours later, there was a magnitude 7.6 earthquake along this Surgu fault zone to the northwest. And so these beach balls show pure left lateral strike slip faulting as sort of the overall sense of slip during these earthquakes. And so we classify these as maybe a doublet earthquake because they're similar magnitude earthquakes occurring, within only about 100 or so kilometers from each other within just a few hours. So we classify them as doublets. And this is a fairly unusual, it's been fairly unprecedented to have a doublet earthquake, which has caused, just so much damage, particularly onshore in a populated area. And just to really emphasize the amount of ground shaking intensity, there was intensity level to 9 recorded, which is, very, some of the strongest ground shaking ever recorded and over a huge area. And I think when you overlay these shake maps onto places where we know, such as the UK, you just see that, the sheer scale of this earthquake, and it gives you a sense as to understand why there was so much devastation covering such a large area and therefore impacting a huge amount of populated areas and people, sadly. So one indication of what actually happened during the earthquake is to look at the aftershocks that really highlight the complexity of faults that ruptured. And so on the right here is just an animation showing how those aftershocks evolved. But on the left here, this static image, we can see all of these different fault structures that ruptured. So it's not just rupture along there's the Eastern Anatolian fault. We've got all of these different splay faults, curved faults, rupture branches or fault branches. And then this rupture on the northwest, second earthquake seems to rupture this sort of horsetail structure. So a huge complexity of ruptured faults that we can really only see because of the dense seismological observations and satellite images that have captured this earthquake in fairly unprecedented detail, I would say. When the first earthquake ruptured, there seems to have been, that would have increased the stress on this Surgu fault, but there was no evidence of sort of precursory foreshock activity along that fault. So how did the rupture initiate? So we look at, beach balls, moment tensors, which represent the average of slip across, those several hundreds of kilometers. But actually what happened right at the start of the rupture is really important to study. And this is some analysis that I've done where we see the rupture nucleated close to this splay fault of the Eastern Anatolian fault. This has been called the Nali fault zone. And the first motion beach ball, so representing the motion along the fault at the very start of the rupture, is actually showing much more of an oblique normal type of sense of slip rather than the pure strike slip mechanism that represents sort of the greatest amount of slip. So it seems like the rupture nucleated with this sort of, different on a splay fault with a, slightly different sense of slip to what we might expect given the regional state of stress. And so some of the work I've been involved in is to look at teleseismic, so global seismic waves of this earthquake, and to really map out the evolution of the rupture in detail. And so these beach balls essentially represent the areas of greatest amount of slip during the earthquake. And this is given here in snapshots over time. So you can see that the rupture initiates along this splay fault, this Nali fault, and then propagates north where it intersects the main Eastern Anatolian fault. The rupture propagates to the northeast. towards the 2020 earthquake, magnitude 6.8, but then begins to propagate backwards to the southwest, so going past where the rupture initiated, and then ends all the way down close to the Dead Sea fault zone. What we see evidence for in the teleseismic slip evolution, based on this plot here, which shows distance from the epicenter against time. You can see these different sort of episodes of seismic slip going first one way along the Eastern Anatolian Fault, then propagating bilaterally in the other direction. And so you can, from these sort of move outs of the slip, you can see, or we can make estimates of the rupture velocity, so how fast the rupture propagated. And so there is some evidence here of very fast slips. So this is a distance time plot, so you work out an approximate rupture velocity, and there's evidence for quite fast ruptures, quite fast rupture in certain places along during the earthquake. And so here's just an animation of that rupture evolution, beginning on the splay fault, then propagated northeast, and then going back to the southwest. So this is a really complex earthquake that I think which is also down to the density of observations that we have these days for such earthquakes. So that's the first earthquake, the magnitude 7.8. We also looked at the magnitude 7.6 a few hours later on the Sergei fault to the northwest. And you can see that this is much more of a compact rupture. So it ruptured a much smaller extent of that fault, and it ruptures over only 20 seconds compared to 80 seconds for the first earthquake. So given that the magnitudes are very similar, we sort of proposed that this is what we call a high stress drop earthquake. So it's rupture. There's a huge stress drop during the earthquake because of the similar magnitude but shorter fault length that's ruptured. And when at the edge of the rupture, we see a rotation of the fault strikes, and also we see a greater propensity for oblique normal fault in earthquakes. So it seems like these earthquakes start and stop with sort of oblique normal faulted mechanisms in this area. So more work has been done by Diego Melgar. This is the first paper we had published in Seismica that uses GPS, local GPS and strong motion seismometer measurements to really look at the fault distribution of the rupture distribution, but during both earthquakes. And they found the rupture velocity to be fairly fast, but not really fast along the first during the first earthquake. So rupture velocity of about 3 kilometers per second. But then for the second earthquake, they definitely see a very fast rupture, what we call a super shear earthquake. So it's a rupture velocity traveling faster than the local S wave velocity, and that's quite an unusual observation. We can also use satellite data to map out the distribution of slip along the fault. So this is work done by Sylvain Barbeau and colleagues. And they've used satellite INSAR measurements to look at sort of the static offsets, comparing before and after the earthquake. And they can, this has a very good spatial resolution of fault slips. This is just a 3D perspective view of the amount of slip along the fault during the first earthquake, and you can see these distinct patches of rupture or of greater fault slip, these asperities which seem to have ruptured, and these probably represent the asperities that ruptured individually during the previous earthquakes in the preceding centuries. What they do note though in this study is that there's a segment of the fault here, about 50-kilometer long segment, that didn't rupture in the 2023 earthquakes, but also didn't rupture during the 2020 earthquake. So they suggest this might be a possible seismic gap and could host a sort of mid to large magnitude 6 in the future. So it's probably a part of the fault which has been stressed during the earthquakes, but that stress has not yet been released. Further work by Delouis et al. This is a group from the University of Nice. They've used local strong motion data to again look at the slip rate along the fault. And so they look at the slip rate in different time segments compared to relative to where the rupture initiates. And they see this sort of move out in both directions along the Eastern Anatolian Fault. And they try to map out the speed of the rupture front. So this is the red line here. So on average, the rupture travels at about 3 kilometers per second, but then it does have these faster segments, like here, little sort of kinks in this rupture front line, which mean a faster rupture velocity. And again, here on the southwestern side, and again here close to the, down towards the Dead Sea Fault. And you can see this also in a back projection of teleseismic P waves, which map out the very front of the rupture. You can see these, on average, it's about 2.5 kilometers per second rupture speed, but there are these sort of little upticks in rupture speed. So it seems like the rupture overall was a fairly average in terms of rupture speed, but it did at certain points encounter certain parts of the fault, which then allowed a much faster rupture speed. So I've talked about super shear earthquakes and why are they so important. So super shear earthquake is like a supersonic earthquake. It's a bit like a supersonic jet generating a Mach cone when that jet travels faster than the velocity of the medium it's traveling in. And so this can happen with earthquakes too. Most earthquakes do rupture speeds lower than that, but it's been predicted by theory, and there are quite a few observations now of super shear earthquakes. And they're important because they tell us something fundamental about the mechanics of the fault zone. And they also impact ground shaking. A faster rupture means more amplified ground motion due to a narrower waveform pulse. And these Mach wavefronts are less attenuated over distance. You can have stronger ground shaking reaching further distances away. And so buildings in the area, for example, could experience both two phases of shaking. So they could experience this fast traveling super shear rupture front, but also the sub-rayleigh, or the more normal rupture front traveling behind it. So that can, of course, increase the chance of damage. But the fault zone properties that control super shear rupture are not fully understood. They tend to occur on strike-slip faults, but previously they were thought to occur more on sort of geometrically smooth and straight faults, like the Northern Anatolian Fault, for example, and maybe along very mature fault zones. This is a rupture simulation done by a group at Caltech and the University of Illinois, trying to simulate what happened to the rupture front during the earthquake. So you can see this propagation along the splay fault, and then the rupture reaches the Eastern Anatolian Fault, where it generates this Mach cone here. But this Mach cone is very transient in nature. It doesn't last for very long in places. So it seems like at certain points where the rupture encounters some sort of geometric complexity or additional splay fault or bend in the fault, again, here you see these multiple rupture fronts. So it seems like this super shear rupture is very transient, and this might have really affected the ground motion during the earthquake. So just to summarize then, dip-slip faulting seems to be more prominent, both the rupture initiation and termination. And it seems like dynamic stresses from that, a fast rupture on the initial splay fault then allowed the rupture to propagate onto the Eastern Anatolian Fault zone, which has implications for strike-slip faults elsewhere in the world. So for example, in California, you could have a rupture initiation on the San Jacinto Fault, which could then trigger a much larger rupture on the San Andreas Fault, for example. So I think this earthquake is really turning our what we thought to be our thoughts about super shear rupture and what controls it around. It seems like these more geometrically complex fault zones might cause stronger ground shaking. Thank you very much for listening.